Okay, thank you very much. So this work came out of the ARC linkage and also just generally hanging out with Juliet and talking a lot about the River Murray and floodplains. So I can skip over this because I've stole these two photos from Juliet's talk, as you probably can see it. But the general message here is about the naturally saline groundwater abutting the River Murray. So you have a freshwater river cutting through saline groundwater. And if I take this picture, which comes from the Monday group of researchers, so we're closing the family loop here, and you can see just in the red circle there that the Murray River is described as gaining. And there's a bunch of other conceptual models about groundwater River Murray interaction. And you'll often see words like bank recharge with floodwater infiltration, or flushing, or short-circuiting, or hyperactive flow, or all sorts of descriptions of the groundwater surface water interaction, and in particular in relation to the presence of freshwater lenses. And AEMs being one of the primary tools for looking at the freshwater lenses, and Tim gave a very nice presentation earlier about looking at how these things are changing and starting to use AEM over timescales. And you can see here, the red is salt and the blue is fresh. And here's another example of a cross-section with AEM data. And there's a whole bunch of processes here. Now we're referring to the flushed zone and so on. So when we started thinking about how the River Murray and the saline aquifers are interacting, we drew ourselves a little conceptual model, and we have this salt water next to the river, and we have the fresh river, and the row if there's the fresh density of the river and the saline and the heavier saline water next to it. And the river, there's evidence of saline discharge in the river because the salinity goes up as you go down the river. So clearly the river is gaining in places. What are the relevant processes? So if you think about the conceptual model, you've got kind of two main forces at work here. You've got a driving head, a hydraulic driving head. So if the aquifer's got a higher water level in the river, then that's by Darcy's law, forcing water into the river. But also have a buoyancy force because the density of the aquifer, that water density is heavier than the fresh water. So there's a buoyancy force also pushing that water into the river. So you've got two forces pushing that water into the river. So I asked the question, will I find a freshwater lens under these conditions? A gaining river with a saline groundwater and a fresh river. Well, the two forces are towards the river. So the answer is, well, what is my hydrogeology intuition telling me if I rely on that? And then no way, right? Because everything is towards the river, the salt, the density, and the hydraulics. So if we find a freshwater lens under those conditions, it must be due to flooding or bank storage or some short-circuit flows or flushing, or maybe the river's not actually gaining, maybe it's losing, or someone's even mentioned paleo freshwater. It could be some of these things, right? But let's just dwell for a second on hydrogeological intuition, because so far everything I've said is based on that. And so I went on the web and I went, let's look up intuition. And I found some of these quotes. So, trust your hunches, they're based on facts, file way below the conscious level. And Einstein, the only real valuable thing is intuition. And then we start getting religious about it. And if prayer is talking to God, intuition is God talking to you. And intuition is seeing with the soul. And one of my favourites, intuition is the highest form of intelligence, transcending all individual abilities and skills. So I take my intuition and I say, it's got to be no freshwater lens under those circumstances, that's it, and we move on with our day. So just for a second, if we ignore our intuition as soulless as that may be, and we ask ourselves, what does the physics tell us? And I've spent a lot of my career working in coastal zones where freshwater and seawater are next to each other and the density effects are there. And I spent half my career being with my intuition proving me wrong and, early on embarrassing myself over and over again before realising I needed to abandon my intuition and work with the physics. So let's take on some sharp interface analysis that would routinely be used in a coastal zone, and let's see whether a freshwater lens can persist. So we'll put the freshwater lens there and we'll make it a stagnant one. So Darcy's law says that if it's stagnant, if that freshwater lens is not moving at all, then that water table should be horizontal. So what are the physical parameters? You have a flow of salt water towards the river, because we said it's gaining. There's a thickness of the river and a thickness of the lens and the thickness of salt water under it, and there's a we put in an x-axis, and there's a distance xl, this length of the lens. And we also put like a resistive riverbed layer, like the river conductance that you might find used in Modflow, and it's got a thickness and a hydraulic conductivity Kr, and we've got these densities. So they're the kind of things that we can label our conceptual model. And I'm going to go through very quickly through some maths, but I'm not going to explain any of it. You don't have to take my word for this, but let's pretend for a minute that I know what I'm talking about. So the difference between the coastal zone and the river is that in the coastal zone, the seawater that you find in coastal aquifers is essentially treated as stagnant, and the fresh water is moving towards the sea. And here we have something the other way around. Here the salt water is moving towards the freshwater, and the freshwater lens is stagnant. So it's like a photographic negative of the other. So to do the same analysis I would use in the coastal zone, I worked in saltwater heads instead of freshwater heads. And that really made my ears bleed. But anyway, so I worked in saltwater heads, and here's Darcy's law based on saltwater heads, and I combine these and I do some integration and I get an equation, and here it is if you care. And then I have to work with a head drop across this riverbed because there's a little conducting layer, and there's an equation for that. And I do Darcy's law across the riverbed. I'm just, and then if I combine those, I get this equation for the flow QS of salt water towards the river based on XL, which is the length of the lens. Which what that means is if you go and you measure the width of a freshwater lens, and you've got these other parameters, which is the hydraulic conductivity, all these parameters are things that Juliet has in her numerical models of these systems, so you can pull them out of there. You can come up with an estimate of the saltwater flow. That's right, or you can even measure them, but I just take Juliet's word for it because she never lies. So if you know that length of lens, but that's a tough thing to know. So what if you don't know that? What if you know this E to B? In other words, a piezo measurement at some distance away from the lens in the salt water, so you've got this head, this driving head towards the river. What if you know that? Well, then you can use that, chuck it in that equation. XB is the distance out to that piezo, and then get a flow of salt water to the river. Okay, so that's the theory. Probably went over everyone's head, that's fine. But how do you use it? Okay, so it's all developed on the same theory that we use in coastal zones. So you go out into the saltwater part of a floodplain, you measure the head, which I'm calling E to B here, at some distance XB, and obtain these other parameters as Juliet's magically obtained them from somewhere, so steal hers. Then you can calculate this flow, QS, and once you've got QS, you can calculate E to SR, which is actually the thickness of salt water up against the river. And once you have the thickness of salt water up against the river, assuming the freshwater lens has about the same water level as the river, you can get the thickness of the freshwater lens. Once you've got QS, which you calculate from the other equations, you can also work out XL by inverting that equation, which means then you can have this freshwater lens thickness. And if you want the lens shape, which is E to S, which is the salt water height below the lens, as a function of X, because this now has X in it here, then this is the equation you would use. Okay, so maybe this is all a load of, yep, and I'm making all this up, and none of this is correct. So just going back to guiding our intuition based on this theory, if we assume that all this is right, and actually while you've got salt water moving towards the river, you can actually have a freshwater lens. We'll just think about the heads for a minute. So Darcy's law says you have to go from high head to low head, moving in the direction of groundwater flow. So do we have that here? Well, we have a E to B, which is the head at the boundary, indicates that the saltwater flow towards the river because it's higher than the river. So there's flow moving towards the river. If we put a horizontal water table on the lens, then the water in the lens isn't moving. But then I ask, do we have a falling head in this direction if this water table is constant? So is the head actually dropping as we go towards the river? Well, yeah, it is, because if you look at a column of water here, as we go towards the river, for a given column of water, there's more fresh water in it, which is lighter. So the total weight of water down the bottom here is less as you go that way because the column has less salt water in it, right? So just from a hydraulics point of view, you do actually have a dropping head in that direction in saltwater head terms because there's more fresh water in the column. So, from the heads, just now if I use my intuition and I think about the hydraulics, this is consistent with flowing salt water and a stagnant lens. So, we chuck the numbers in for Mertho, grab some numbers out of some reports. They're up there. Not going to go through them. And we threw the numbers into the equations, and we got a lens that looks about that, about 400 metres from the riverbank, and the AEM is something like that. That's not a horrendous estimate of the freshwater lenses that are found there, despite there being a gaining river in places. So you have to turn that around because the freshwater is actually on the other side, and I can't be bothered redrawing that figure, so I'll just flip it over. Okay. You're more impressed by my animation than again by my maths, but anyway. So do we always get a lens near a gaining river? So is this just a given? So I plotted here with the head, at the head in the aquifer, and this is it. This is the difference in head in the aquifer between the aquifer and the river. So this is a 4 metre head difference and a 6 metre and 2 metre at some distance. And this is the length of lens. So at some point this curve reaches 0. So if the head in the aquifer for all the other parameters is say 1.5, there's no lens. So the head in the aquifer has to be less than 1.5 for all the other parameters I use to gain this curve for there to be a lens. And obviously a negative lens is just mathematical obscurity. Okay, so the nice thing about this equation is we can start saying what are the parameter combinations by which you get a freshwater lens despite the river being gaining. And, okay, so even all of that could have been garbage, right? I could have made even all of that up. You still don't believe me? So we went into the sand tank lab and we've got a sand tank with reservoirs on the other side and we dyed the water and made it salty. And that's what we got right there. So here's our saltwater aquifer here, and there's the freshwater river. Of course, it's not nice and clear because that salt water's going in, and we were flushing that out continuously, but it does stain the water a little bit. Nothing like this, of course. And that's the analytical solution, and there it is there. So salt water's moving towards the river. The density forces in that direction, the advective forces in that direction, and there's a stubborn little bit of fresh water there that won't go away. Okay, so conclusions, who cares? Well, here's the reason why you might want to care. So despite the forces being in a direction that you would figure there should be no freshwater lens, with a gaining river, saline groundwater acting towards the river, in fact, a stable freshwater lens can exist there due to the buoyancy forces. The analytical solution gives us some simple equations to get a first kind of estimate at it. So if you have these parameters that are fairly readily available for a lot of sites, we can kind of say, well, if it's gaining, should there be a lens or shouldn't there? The implications are that if you find freshwater near a river, it doesn't mean that the river is losing. In fact, the river can be gaining and you have a freshwater lens there at the same time. And from some of the diagrams I've seen, this could mean a little bit of redrawing or reconceptualizing, and it just adds another process or another potential driving force for freshwater lenses in these systems. And we study the steady state sharp interface situation, and we look at whether the lens can persist. We assume that it's there. We didn't look at what causes the lens to form. We got some hints at it when we did the sand tank modelling, because when we constructed the sand tank in a certain way, we tried to get the situation going, the lens wouldn't form. So whereas we constructed it a different way, the lens would form and then stabilise. So just because it's there doesn't mean it will grow to that position under any conditions. There's something about the growth of the lens. But anyway, they will at least persist if everything else is stable. And thanks to Juliet and Tariq for their help. That's it. Thanks, Palmer. Yeah, that's a good question. We've given that some thought. So if you add ET, then the freshwater lens head will slope away from the river, and then there'll be a flow in the lens. Because if you extract anything, because that lens has no water coming out of it, it's got no water going into it, it's just stagnant. So if you take any water out of it, you'll invoke a slope. So it probably won't extend as far, and then there'll have to be circulation coming out of the river to keep feeding it. So those kind of things are definitely areas for future work, for sure. Yeah.
And is there a critical measurement where it's classified as freshwater, or the difference between freshwater and saltwater that needs to stay there?
The analytical
solution. They are value salinity.
Yeah. The analytical solution has a ρF, which is the density of the freshwater, which is based on the salinity. and the seawater has a rho s. So, in fact, you could have any of those two densities, and it doesn't really matter from the analytical solutions point of view. You could have half seawater and seawater, or 1/1,000,000th seawater and twice seawater. It doesn't really matter. Buoyancy forces work as long as you've got two waters of different densities. It's just that the closer in salinity, or therefore the closer in density they are, then you'd have less of a driving force for that freshwater lens to be there. So if you plot a graph versus the size of lens compared to density ratio, you can actually see what density ratio you need for a freshwater lens to be there. So in fact, your intuition on this account is correct, that in fact the density ratio is a key driver of the lens being.
We are out of time, so
Thanks, Bob.
one question